All right. Hello, everyone. We are Group Decisive Hit, and my name is Junong, and I'm here with Wenbing. So we are working on the problem statement one, which is the smart port operation, AI for horizontal transportation, a transport optimization. All right. So what is our objective? Our objective is to complete a total of 20,000 jobs, which is 2,500 per QC, using a fleet of 80 HT in the shortest amount of time. So now let's compare what we did with the original code. So first we have smarter HT assignment. So the default code, it will choose the first unselected HT from the left for the DI and from right for the LO, which is purely positional. Which whereas ours we pick the nearest available HT to the next pickup using lane legal macro path, which for DI, we find the minimum path length from the HT buffer slot to the QC in. Whereas for LO, we find the minimum path length from the HT buffer slot to the yard in. And why does it matter? It's because it cuts empty travel, reduces cross traffic on one-way lane, and accelerate first byte latency for each job. So for our second point, we have a optional smart yard choices for DI. So with the default code, it only uses the provided yard only, whereas ours we have a toggleable option which the DI can choose the closest yard among the closest one and three other alternative if it's present. So for safety reasons, we usually keep this off by default, but when you turn it on, we recommend a tiny 700 DI cap guard per yard so you never exceed the hard limit. And for the third one, we have a deterministic lane legal macro routing for all four legs. So for both versions, there's a build path for these four legs, which is buffer to QC in, QC out to buffer, buffer to yard in, and yard out to buffer. So what we tighten is that we consistently use the same one-way corridors for each leg. And so the every HT would follow predictable flows. And we also added a tiny helper to help to keep HT parked on a Y equals 6 with X clamp, which is the buffer zone. And this avoids illegal slots with reduced path jitter around the buffer reentry. Now I'll move on my time to Ming.
Okay, so the next comparison is about the throughput guard, which is max job per planning tick. So by default, the job planner will plan all plannable job in the loop, and the comment claims that at most 16 job per loop, but it doesn't enforce in the appendix, so we make it tunable to optimize the workflow. So for this terminal, we found 64 is the best, and you will see the log line plan 64 new jobs. So that larger batch fully primes the 8-stage pipelines and keeping QCs and yards continuously busy. Yes, and why this matter is because it prevents bursty assignment that can stuff slower resources and keeps the simulation stable and reproducible. Yeah, to maximize and to optimize the overall workflow. And the last part is about presentation toggles for ablation. So we keep 3 switches to make the ablation transparent. The first one is use nearest HT. So we keep this on, and it will choose the closest HT to the pickup. Turn it off to reproduce the baseline left-right pick. So as the image shown below here will be the uh, off off version of output, and it is slower than the output we get, and we'll show it the output for on later on. And the second is smart yard choice, which will, as we mentioned, we keep it off because the alternates didn't help on these maps. And we keep data sets yards for DI and show smart yards and as a tunable features. And the third one is max job per ticks, and we'll keep it as 64 because we found this is the best output. Yeah, our best admission rate here. So yeah, move on, we'll show the result. And the default code for the result is 1.16 million, and what we get is 1.006 million. Yeah, this one is with the use nearest HT on. So it is obviously faster than off option, and we get an improvement for 13 and 76% overall. Okay, so move on to the limitation for our current build. The first one is distance only HT choice. We pick the nearest HT to the next pickup, but don't factor predicted weights at QC or yards or corridor congestions. So this can be suboptimal when resources are temporarily saturated. And the second one is smart yard off. So we keep data sets yards for DI because alternates didn't help on this map. That means we don't exploit potential proximity wins when they exist. And the last one is hard-coded macro routes. Because these four routes builders encode lane geometry and procedurally. So if the map changes, the line direction and new connector will change also. Means we need to means the path need to manually edit it. Yeah. So I think that's all for our presentation. Yeah, we are from Decisive. Thank you.